Fatin Binti Muhammad Fadzil.
di 2018-2085-854.
Expansion of mathematical science that began in the 19th century result from economic growth fueled by industrial revolution. 20th century advancement of math are often alongside technology, research and scientific innovation. Mathematics is considered a science and absolutely joined to other theoretical and applied science, including physics, biology, chemistry, geology, economy, engineering, architecture, political science and social science. The most important invention of interdisciplinary science is the electronic programmer computer. The computer not only requires advanced mathematics for its development, but also provides solutions to complex mathematical problems where the computation required to solve problems exceed human capability. By the end of 20th century, there are hundreds of specialized areas in mathematics, and the mathematics subject classification was dozens of pages long. Published mathematical journal continues to increase in number and content.
Hello and Assalamualaikum. My name is Norsyahirah Alia Binti Muhammad Shukri di 2081208669. Hilbert's problem. What is the Hilbert's problem? Hilbert's problem are 23 problems in mathematics published by German mathematician David Hilbert. The problems were all unsolved at the time, and several of them were very influential for 20th century mathematics. Hilbert presented 10 of the problems, which are 1, 2, 6, 7, 8, 13, 16, 19, 21 and 22 at the Paris Conference of the International Congress of Mathematicians, speaking on August 8 in the Sorbonne. The complete list of 23 problems was published later, most notably in English translation by Maury Frances Winston Newson. This is picture of David Hilbert. The nature and influence of the problems. Hilbert's problems range greatly in topic and precision. Some of them are propounded precisely enough to enable a clear negative answer. This is example of the Hilbert's problem. The 8th problem concerns about prime number theorem. 11 and 16 problem concern what are now flourishing mathematical subdisciplines like the theories of quadratic form and real algebraic curve. 6th problem concern the axiomatization of physics, a goal that 20th century developments of physics. 4th problem concern the foundation of geometry in a manner that is now generally judged to be too vague to enable a definite answer. Next, the 17th problem represents of definite form by square. The 24th problem. Hilbert originally included 24th problem on his list, but decided against including one of them in the published list. The 24th problem was rediscovered in Hilbert's original manuscript notes by German historian Rudiger Thiel in 2000. For the summary, 1 on the cleanly formulated Hilbert's problem, which are 3, 7, 10, 11, 14, 17, 19, 20 and 21 have a resolution that is accepted by consensus of the mathematical community. On the other hand, problems which are 1, 2, 5, 9, 15, 18, and 22 as solutions that have partial acceptance, but there are exists some controversy as to whether they resolve the problem. Its problem, the Riemann's hypothesis, 12, 13, and 16's problem unsolved. Next, 4th and 23's problem are too vague to ever to be described as solved, and the Dovitram 24 problem will also be in this class. 6th problem is deferred as a problem in physics rather than in mathematics.
Assalamualaikum dan selamat sejahtera. Nama saya Nurul Adlina binti Mohd Zamree bernombor matrik di 2018 208 5878 dan hari ini saya akan bentangkan tentang the consistency of arithmetic.
The consistency of arithmetics. So in mathematics, Hilbert's second problem was posed by David Hilbert in 1900 as one of his 23 problems. It asks for a proof that the arithmetic is consistent and free of any internal contradictions. Hilbert stated that the axioms he considered for arithmetic were the ones given in Hilbert 1900, which include a second-order completeness axiom. In the 1930s, Kurt Gödel and Gerard Gentzen proved result that cast new light on the problem. Some feel that Gödel's theorem gives a negative solution to the problem, which others considered Gentzen's proof as a partial positive solution. Hilbert asks, when we are engaged in investigating the foundations of a sign, we must set up a system of axioms which contains an exact and complete description of the relation subsisting between the elementary ideas of that sign. But above all, I wish to designate the following as the most important among the numerous questions which can be asked with regard to the axioms. To prove that they are not contradictory, that is, that a definite number of logical steps based upon them can never lead to contradictory results. In geometry, the proof of the compatibility of the axioms can be effected by constructing a suitable field of numbers such that analogous relation between the numbers of this field correspond to the geometrical axioms. On the other hand, a direct method is needed for the proof of the compatibility of arithmetical axioms. Hilbert's statement is sometimes misunderstood because by the arithmetical axioms, he did not mean a system equivalent to Peano arithmetic, but a stronger system with a second-order completeness axiom. The system Hilbert asked for a completeness proof of is more like second-order arithmetic than first-order Peano arithmetics. As a nowadays common interpretation, a positive solution to Hilbert's second question would in particular provide a proof that Peano arithmetic is consistent. There are many known proofs that Peano arithmetic is consistent that can be carried out in strong systems such as the Mello-Frankel set theory. These do not provide a resolution to Hilbert's second question. However, because someone who doubts the consistency of Peano arithmetic is unlikely to accept the axioms of set theory to prove its consistency. Thus, a satisfactory answer to Hilbert's problem must be carried out using principles that would be acceptable to someone who does not already believe Peano arithmetic is consistent. Such principles are often called finististic because they are completely constructive and do not presuppose a complete infinity of natural numbers. Gödel's second incompleteness theorem places a severe limit on how weak a finististic system can be while still proving the consistency of Peano arithmetic. Gödel's incompleteness theorem. Gödel's second incompleteness theorem shows that it is not possible for any proof that Peano arithmetic
is consistent to be carried out with piano arithmetic itself. This theorem shows that if the only acceptable proof procedures are those that can be formalized within arithmetic, then Hilbert's call for a consistency proof cannot be answered. Genzen consistency proof. In 1936, Genzen published a proof that piano arithmetic is consistent. Genzen's result shows that a consistency proof can be obtained in a system that is much weaker than a set theory. Genzen's proof proceeds by assigning to each proof in piano arithmetic an ordinal number based on the structure of the proof, which is of this ordinal less than epsilon number. He then proved by transfinite induction on these ordinals that no proof can conclude in a contradiction. The method used in this proof can also be used to prove a cut elimination result for piano arithmetics in a stronger logic than first order logic, but the consistency proof itself can be carried out in ordinary first order logic using the axioms of primitive recursive arithmetic and transfinite induction principle. They give a game theoretical interpretation of Genzen method. Genzen's consistency proof initiated the program of ordinal analysis in proof theory. In this program, formal theories of arithmetic or set theory are assigned ordinal numbers that measure the consistency strength of the theories. A theory will be unable to prove the consistency of another theory with a higher proof theoretic ordinal. Lastly, the modern viewpoint of the status of the problem. While the theorems of Gödel and Genzen are now well understood by the mathematical logic community, no consensus has formed on whether these theorems answer Hilbert's second problem. Simpsons argued that Gödel's incompleteness theorem showed that it is not possible to produce finististic consistency proof of strong theories. Kreisel states that although Gödel's result implied that no finististic syntactic consistency proof can be obtained, semantic argument can be used to give convincing consistency proof. Deblassens argue that Gödel's theorem does not prevent a consistency proof because its hypothesis might not apply to all the systems in which a consistency proof could be carried out. Dawson called the belief that Gödel's theorem eliminates the possibility of a persuasive consistency proof erroneous, citing the consistency proof given by Genzen and later one given by Gödel in 1958. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Tuan Nurfarah Hamizah, Binti Tuan Shari, metric number D201810833270, and I will present about the real analysis and topology.
For the first one is real analysis. So what is meant by real analysis? In mathematics, real analysis is the branch of mathematical analysis that studies the behavior of real numbers, sequence and series of real numbers and real function. Some particular properties that real value sequence and function that real analysis study include convergence, limits, continuity, smoothness, differentiability, and integrability. Basically, real analysis is what we have learned in calculus. So, let's learn about history of real analysis. For the first one is method of exhaustion. Archimedes made more explicit but informal use of the concept of limit and the convergence when they used the method of exhaustion to compute the area and volume of region and solid. The photo shows that Archimedes used the method of exhaustion to compute the area inside a circle by finding the area of regular polygon with more and more sides. This was an early but informal example of limit, one of the most basic concepts in mathematical analysis, and this is the result he obtained with the method of exhaustion include the area bounded by the intersection of a line and a parabola, the area of an ellipse, the volume of a sphere, and the volume of a cylinder. Next, the Chinese mathematician Liu Hu used the method of exhaustion in the 3rd century to find the area of a circle. Zhu Chongzi established a method that would later be called Cavalieri principle to find the volume of a sphere. The second one is theory of integration. In the middle of 19th century, Riemann introduced his theory of integration. The last third of the century saw the arithmetization of analysis by Weierstrass, who thought that geometric reasoning was inherently misleading and introduced the epsilon delta, which is the definition of limits. The photo shows the integral of as the area of a region under a curve. The next one is the Hilbert space. In the early 20th century, calculus was formalized using an axiomatic set theory, and the Hilbert introduced Hilbert space to solve integral equation. The next one is topology. In mathematics, topology is concerned with the properties of a geometric object that are preserved under continuous deformation, such as stretching, twisting, crumpling, and bending, but not tearing or gluing. One of the topological history is problems of Königsberg 7 bridges. The city of Königsberg in Prussia was set on both sides of the Prussia River and included 2 large islands which were connected to each other or to the 2 mainland portion of the city by 7 bridges. The problem now was to devise a walk through the city that would cross each of the bridges once and only once. Euler have proved that the problem have no solution. He replaced length with vertex and bridge with edge, and which only serve to record which pair of vertices is connected by that bridge. Further, if there are no or 2 nodes of odd degree, then any Euler path will start at one of them and end at the other. For Euler circuit, it will start on same and end with the same node. All of Euler circuits are also Euler paths, but not all Euler paths are Euler circuits. The second one is Euler polyhedral theorem. In the history of topological development, some well-known and important theorems about polyhedra and Euler are also relevant. The theorem reads, if the sum of the vertices of a vertex is vertex, the number of edges, the number of faces, then they always have any relation, which is V plus F minus E equal to 2. The last one is Riemann-Riemannian geometry. Riemann-Riemannian geometry analyzes the concept of topology as the basis for function theory rather than promoting topological progress. In 1851, the German mathematician Bernhard Riemann considered surface related to complex number theory and hence utilized combinatorial topology as a tool for analyzing functions. Riemann geometry was put forward in generality by Bernhard Riemann in the 19th century. It deals with a broad range of geometry whose metric properties vary from point to point, including the standard types of non-Euclidean geometry.
Hai, nama saya Qamarina Dayana. Saya akan membentangkan tentang Theory of Games, Computer Science. Teori permainan atau dipanggil game teori adalah kajian model matematik interaksi strategik di antara memilih keputusan yang rasional. Ia mempunyai aplikasi dalam semua bidang sains sosial dan juga dalam logik, sains sistem dan sains komputer. Pada asalnya, ia membahas permainan sifar jumlah atau zero-sum games, di mana kemenangan atau kekalahan setiap peserta seimbang dengan yang dilakukan oleh peserta lain. Teori permainan moden dimulakan dengan idea keseimbangan strategi campuran dalam permainan zero-sum game dan dibuktikan oleh John von Neumann. Kemudian diikuti oleh buku 1944 Theory of Games and Economic Behavior yang ditulis bersama dengan Oscar Morgenstern. Jadi ni adalah buku-buku mereka. Terdapat 13 jenis game iaitu kooperatif atau non-kooperatif, symmetric atau asymmetric, zero-sum atau non-zero-sum, simultaneous atau sequential, perfect information and imperfect information, combinatorial games, infinitely long games, discrete and continuous games, differential games, evolutionary game theory, stochastic outcomes, meta games, and pooling games. Tapi saya akan terangkan cuma 5 jenis game. Yang pertama ialah kooperatif atau non-kooperatif, atau dikenali sebagai kerjasama dan bukan kerjasama. Cooperative game ni ialah permainan dapat membentuk komitmen yang kuat, manakala non-cooperative game pula permainan tidak dapat membentuk pakatan atau kerjasama. Game ini sesuai untuk permainan berkumpulan. Yang kedua ialah simetrik atau asimetrik, iaitu permainan bergantung pada strategi dan bukannya bergantung kepada pemain. Yang ketiga ialah zero sum atau non-zero sum, iaitu pemain tidak dapat menambah atau berkurang. Contohnya permainan ialah poker dan catur. Yang keempat pula ialah simultaneous atau sequential. Simultaneous game ialah permainan serentak, iaitu permainan di mana kedua pemain bergerak serentak atau jika mereka tidak bergerak serentak, pemain kemudian tidak mengetahui tindakan pemain sebelumnya. Contoh permainan ialah rock paper scissors. Sequential game pula adalah permainan di mana pemain kemudian mempunyai pengetahuan tentang tindakan sebelumnya. Contoh permainan ialah catur. Yang terakhir ialah combinatorial game, iaitu permainan di mana kesukaran mencari strategi yang optimum berpunca dari banyaknya kemungkinan gerakan disebut permainan combinatorial. Contoh catur. Representation of games atau perwakilan permainan. Terdapat 3 representation of game, iaitu extensive form, normal form and alternative game representation. Extensive form dapat digunakan untuk memformalkan permainan dengan urutan waktu pergerakan. Contohnya seperti gambar ni. Setiap bucu mewakili titik pilihan bagi pemain. Yang kedua ialah normal form, iaitu permainan yang berbentuk strategik. Biasanya diwakili oleh matriks yang menunjukkan kepada pemain strategi dan hasil. Yang ketiga ialah alternative game, iaitu bentuk perwakilan permainan alternatif dan digunakan untuk beberapa subkelas permainan atau disesuaikan dengan disiplin permainan. Selain perwakilan permainan klasik, beberapa perwakilan alternatif juga menyediakan aspek yang berkaitan dengan masa. Contohnya seperti dalam tabel di bawah ni.